Today I want to discuss with you how we can put all of these ideas together. So we're going to talk about putting it all together today. And what we want to do is focus on the ways in which the amplitude, the period, and the phase shift, as well as the vertical shift all combine together, and how we can approach these kinds of problems when we're working to graph functions or when we're working to write the equations of functions. So let's go ahead and look at the object of our attention today. What we're looking at is sort of the general trig function. We discussed this in class earlier, but the general trig function that we're going to work with will either be a sine or a cosine, and again later on we'll explore some other trig functions. There are basically four things that we can do with this trig function. We can change the amplitude, we can change the period, we can change the phase, and we can change the vertical height. And all of those show up as values, as constants that can be made to be any value inside of our trig function expression. So let's take a look at an example problem where all of these pieces are given, and we have to graph a function that has all of these different changes. So our example that I would like us to start with today is the function y equals 2 times the sine of 3x minus pi plus 1. And as you can see, this has a amplitude, period, vertical, and phase adjustment. All of these things are going to be different from the traditional function. Nevertheless, I'm going to start with the basic parent function and see where things go from there. So here's our standard interval of 0 to 2 pi. And let's go ahead and look at the basic trig function that we want to look at right now. So again, by now this should be old hat 2. This is the function that we're working with. This is the sine graph on the interval from 0 to 2 pi. The standard graph has an amplitude of 1 and a period of 2 pi. Now I'm going to go through and make all of these changes, all of these adjustments to this graph, and we'll do them not more than one or two at a time. To start with, I'm going to look at the parameters that my graph has to fit into, and those are these external pieces right here. So the amplitude and the vertical shift are the pieces I'm going to focus on first. Those will sort of define the envelope and where my trig function has to fit in. The plus 1, this vertical shift here, tells me that my trig function will now oscillate about the line y equals 1 here. This will be the center of my oscillation. And the amplitude here of 2 tells me that my function will go 2 units above and 2 units below this graph, or below that center line. So here you can see I already have a general idea of what my graph will be doing, and I know where my graph should be fitting. What we need to do now is come up with more specific values of the shape, and that's a result of determining what the period is and determining what the phase shift is. So my period in this particular case is 2 pi over k. In this particular case, that will be 2 pi over 3. Now 2 pi over 3 is not a value that is clearly marked on my graph yet, so we need to take and look at this. This value here is pretty close to 2 pi over 3, so I'm going to have one period of my graph fit in this particular section right here, and 4 pi over 3 is going to roughly be right here. So I'm going to have another period in there. You can see that I'm going to have 3 separate graphs of this trig function all in here. And I'm going to sketch this graph now with just the amplitude, vertical shift, and period changes, and then we'll worry about the phase shift in just a moment. So because this is sine, I know that it starts at the center line, will go up to a maximum through the origin, or through the 0 of my oscillation, and back down to a minimum before coming back up at the end of the period. So we can simply rough in what the values will look like here, and then we can draw ourselves a smooth curve that will represent a general sketch of this function. So I'm going to expect my graph to look something like this. It's not perfect, but it definitely illustrates a general form for the graph of y equals 2 times the sine of 3x plus 1. And notice the only thing we have yet to incorporate is our phase shift. Once we get the phase shift down, we can go ahead and compute the final graph. Our phase shift, in this particular case, our phase shift will be the value minus c over k, c being the minus pi. That changes the numerator to a positive, and the k value of 3. Our graph will be shifted pi over 3 units to the right. So now we have to go further and shift this over pi over 3 units. Well, this is pi over 3 units right here. From here to here is pi over 3 units. So this entire section of the graph will be shifted over. And we can now go ahead and sketch in what our graph will look like. And the final graph then, if we start here, the final graph will look something like this. And oftentimes we'll see this kind of interaction between the period and the phase to where things work out relatively nicely. And just so you can see this more clearly, oftentimes it's helpful when you're doing these on your own to have a highlighter. This is the function that is our final answer here. This is the function y equals 2 sine of 3x minus pi plus 1. This is our final function. And again, the way we came up with this was to go step by step through the various changes. Trying to do all of these at once would be very overwhelming. It would be very difficult to come up with this graph. One of the skills that we haven't spent a lot of time talking on, which is almost as important as being able to graph these functions, is to be able to take a graph and write the equation. And this is a little bit more difficult skill, but something that we can master pretty easily in doing much the same thing that we have been doing already. So writing equations from graphs involves a little bit more work. And one of the things, as we discussed earlier, we can often take and consider something either a sine or a cosine graph, depending on whatever is most convenient. And I actually have a sample graph here that I would like us to look at today and see if we can come up with the equation for this graph. This is a fairly complicated graph, but there are several things that we can do to get started on coming up with an equation for this graph. One of the first things to notice here is that the maximum amplitude of the graph is 1, the minimum amplitude is minus 5. So this graph extends from positive 1 all the way down to minus 5. Halfway in between those two, halfway in between minus 5 and 1, is the value minus 2. So we can think about this graph, this line right here. We can think about this line here as though it were our center line. This is the graph. This is the axis that the graph oscillates above and below. And you can see that must be the center line because it goes up and down an equally large amount from both of those places. Therefore, if we were to think about what this function would look like, we still don't know whether we're going to treat this as a sine or a cosine graph. But we know that if we're writing the equation, this is going to be y equals some amplitude. We'll have some trig function in there. We know that we're going to have a vertical shift of minus 2. The graph is shifted 2 units down. That's where the central axis is. And we actually already know that it's going to be shifted, or it's going to have an amplitude, rather, of 3 units. It goes 3 units above and 3 units below that center line. Now let's take a look at our graph here a little bit more closely and see if we can notice any other features. Well, one of the features we notice is that in going from x equals 0 to pi over 2, notice we have one period. There's one complete period on the graph here between these 2 points. So the period of our graph is pi over 2, and that allows us to determine another feature of our graph. If our period is pi over 2, and this is supposed to be 2 pi divided by k, really what we're interested in here is determining what k value multiplies x. We can work out what that k value has to be here. We can start by cross multiplying here. I get pi times k is equal to 4 pi, and clearly the only way that can be true is if k is 4. So now we have 3/4 of our problem done. We can now go on to think about the phase shift and what kind of trig function we want to do to describe this. So again, notice what I did is I found one complete period of my trig function, and I used this relationship then to determine what k value would give me that correct period. Going back to our graph now, we'd like to come up with the phase shift, and there are several ways of approaching the phase shift here. This is a place now, the phase shift is where we need to decide what kind of trig function we're going to work with. And let's actually go through and write this equation as both a sine function and as a cosine function and see how they differ, see what kind of differences we can see in these graphs. Notice that if this were to be a sine graph, that this point would normally be, if there was no phase shift, this point should be at x equals 0. So the phase shift is simply this distance right here. Let's go ahead and mark that distance for our phase shift. Our phase shift goes from here to here. That distance is one phase shift if we're thinking about this as though it were a sine graph, because sine starts at the center of oscillation and goes upward. And if you look, you can see that we have pi over 4 here, and pi over 8 is conveniently marked here. So this would be a graph that has a phase shift of positive pi over 8. So we can use that information then to give us our c value. Recall that our phase shift, in this particular case, we would like it to be pi over 8, should just be equal to minus c over k. So again, we're going to set up a ratio of the phase shift we want to our definition, and recall that k is 4, so this looks like pi over 8 is equal to minus c over 4. And this then, if we solve this equation, tells us c must be minus 4 pi over 8, or minus pi over 2. And therefore, coming back up to our original function, if we choose this to be a sine graph, we would have a phase shift, a c value of minus pi over 2. And this should be the function. This should be the function that we have on this graph. I believe that's the graph that I asked the computer to create. And, oops. And here, in fact, you can see we do have this graph, 3 times the sine of 4x minus pi over 2 minus 2. Again, we approach this problem the same way we would if we were graphing it. We break it down piece by piece. It's too difficult to try and find the entire graph in one step. We want to go through and find the bits and pieces, the parts of the transformation that go to create this. Well, what about looking at this as a cosine graph? What about looking at this as a cosine graph and seeing what we would get as a result of treating it like that? If we treat it as a cosine graph, we have a different phase shift. Yeah? We have a phase shift that goes this far to pi over 4. So the only thing that would be different if we express this as a cosine graph is that we would have a phase shift of pi over 4 as opposed to pi over 8. And that would simply change our c value. We can see that if we go through and look at this example again. If we want a phase shift that is equal to positive pi over 4, that's going to be equal to our minus c over k. The k value stays the same, right? The period is the same, whether we're talking about cosine or sine, the period is the same. So this simply says that pi over 4 is equal to minus c over 4. And very quickly we can see that c must equal simply minus pi. Everything else stays the same. So if we wanted to write this graph as a cosine graph, this would be the graph y equals 3 times the cosine of 4x minus pi minus 2. That would be another way to express this graph. I hope this example has been helpful to you. You've been able to see ways to approach these problems in an organized way that will give you a little leg up when you try to write these equations.